Recording is rolling. Today is Thursday, October 20th. So you guys know tomorrow I'm gonna pick up your guys' homework, which was just you guys remember this page? Okay, double-sided. Okay. So one side we covered one day with the Kahoot, answered all these conceptual questions, and on the other side, last couple days we've been solving some of these problems. Okay. So just turn that in by tomorrow. You could turn it in today if you want to. I also just gave you guys your next take-home quiz. Okay, so this open notes take-home quiz looks like this. Okay, you guys got this? I think I got one to everybody. Okay, so I'll give you guys a few days. You can turn it in Monday. Tell you what, if you want to knock it out tonight and turn it in tomorrow, then you don't have to worry about it over the weekend. So you can do that if you want. Take questions, right? Oh, next deal, food drive. So got this flyer. You guys see that cardboard box by the door? Food drive. So if you guys want to bring anything in, this is I think the due date November 18 is what was figured out by the email. So next few weeks, if you guys bring any food in, you can throw it in that box, and somebody will be happy to eat food. Oh, right. So maybe today's going to be this turntable app. I gave you guys this page, but right before I do that, I want to do another problem that involves circular type motion, which I've been wanting to get to, which is a really cool problem. It involves cars on a banked road. So let me flip the screen over here. See, share screen 2. And here we go. Cars on wall. All right. Oh, we got some cars down there. Some motorcycles. Whoa, look at those motorcycles go. Look at that banked road. You guys see that banked road? That is a really steep bank. Just eyeballing it, that might be something like 70 degrees to the horizontal. Just guessing something like that. It's not exactly vertical, but it's getting pretty close to that, right? Hey, do you think those motorcycles there, if they were going too slow, do you think they would probably kind of tend to drift down the wall? If they're going too fast, they're going to kind of tend to drift up the wall, right? So there's probably like some equilibrium speed, you guys think? Right, so like some optimal speed to like not really drift down or up. Oh, you guys want to see these cars do the same thing? Now, before you guys see the cars, I'm going to pause this right here. Do you guys think the cars are much more massive than the motorcycles? Right? Okay. So if the cars are doing the same trick, the cars are much more massive. Do you think the cars would have to go faster, slower, or the same speed as the motorcycles to also maintain that radial size? Let me see, show of hands. How many of you guys think that more massive car has to go faster? Who thinks the more massive car has to go slower? And who think the more massive car has to go probably about the same speed? Well, we're about to find out. Let's see. And he's getting up there. Looks like about the same speed, I think. Does that look about the same speed? I think it is. I think it's the same speed, right? So what we're about to do here in a minute is I'm going to flip over and show you guys the solution of how you solve it. The question could be, what is that speed, right? Given maybe like the angle of the wall, like what is it banked at? What is the radius of curvature? My computer froze. That's okay. You guys saw enough of it. You guys can figure that out, right? All right, so disconnect. All right, let's go ahead and flip back over. All right. My whole computer's frozen. Okay, no, we're good. We're back. All right, so you guys saw enough that, so maybe given, say like the bank of the road, what angle is it at? What is the like radius or curvature the car is going around? And also what is the gravity field? Maybe the planet possibly matters. So here's what we do. I'm just gonna show you guys the solution. It's actually a really quick solution for the setup. It's all on this page, right? Here's the answer right here. We'll sort of, it's the expression that could lead to the answer. Right, so what we've got here. So here's the car. Now, our point of view is like we're behind the car, we're watching it go kind of from the camera point of view. You guys see like the tail lights and the license plate hold on, right? So it's the car's like going into the page and like making a left-hand turn, like going like into the page and around. You guys can see that, right? And notice why I titled this. It said inertial frame of reference, and that's from the point of view of the camera. Inertial frame of reference means like a non-accelerating frame of reference. See, like if you were inside the car along for the ride, you would be in an accelerating frame of reference because you're going around a curve, right? So there's a net force, right? But from the camera's point of view, the camera can watch this whole thing play out. All right. So there's only two forces on this car. There's its weight trying to pull down, which I'm calling mass times gravity field, right? Okay, so there's this weight pulling down, and there's also a normal force from the road. Now, so far in this class, we usually have flat roads, just level roads, in which case the normal force just matches the weight. But that's not going to be true on the baked road. Normal means perpendicular. Okay, you guys see how the normal force is perpendicular to the surface? Okay, I've got a really steep thing, just like the video. So this just eyeballing it might be, I don't know, maybe like 70 degrees. Hey, do you think that angle is also probably about 70 degrees? Do you think it always matches this thing? I think so. Okay. And what I can do is I can take this normal force, break it into components, say, well, how much is that normal force going up against gravity versus how much is it like pushing the car into a circle? Okay. Because the up against gravity, you guys see that the upper component of the normal force that I dashed right here matches the weight of the car, right? So that's going to balance out the car like vertically, right? And there is a horizontal component that's not balanced by anything because that is the net force. I mean, there has to be a net force because the car's on a curved path, and there it is, right? So if I start to apply equations, you can say, again, there's only two forces, the weight and the normal force. The normal force I break into components, right? So if this angle is this angle, then this is the cosine component of the normal force, right? Normal force times cosine of the angle. And this component is the sine component, right? The normal force times the sine of the angle, flips over to the opposite side, right? And you know what else those are equal to? The cosine component, I just mentioned this a moment ago, is equal to the weight, right? So I can say normal force times cosine theta is equal to the weight, right? Balance that out, right? And the sine component is the centripetal force, and you guys have an expression for centripetal force that you guys got from a recent lab, right? With the Play-Doh canisters and the PVC pipe and string, which is mv squared over r, right? So I can write those expressions over here. I can say, I just copy and paste that expression right there. The sine component of the normal force is the centripetal force. And the cosine component of the normal force has to balance it with the weight. Okay. So I have a system of equations. Here's one equation. Here's the other equation. Okay. Now, different things you can do with this, but a quick thing you can do to get to some kind of solution is you can just divide the two equations. I put little curly brackets here to say a system. Right, I got two equations. Okay. I divide the two equations. The normal force cancels out. Okay. And guys, do you guys know what sine of an angle divided by cosine of that angle is? What is sine divided by cosine? Tangent. You guys remember tangent? Okay, so we got tangent of the angle, right? And then all this stuff. Hey, the mass cancels out, which you guys just saw evidence of that because the motorcycles and the cars were going the same speed. So whatever that speed ends up being has nothing to do with that individual mass. Mass canceled out, right? And see that divided by that ends up being this expression. All right, so now we have an expression that relates four variables: the angle of the bank of the wall, the gravity field of the planet, this radius to curvature. Oh, I forgot to point out radius to curvature, but can you guys see like an axis right here? And the car is like basically going around that axis. Right. Here's the radius. Radius, right? Right. That's what that R is, and therefore that R is. Right? And here, V, that's the speed of the car going into the page. If you know any three of those, you could solve for the fourth. Right? Just a little algebra away. So there you go. Right? That's one way to solve that. There's another way to solve this from a dynamic equilibrium point of view. Like if you're inside the car, you perceive a centrifugal force, which is a term I almost never use, but so probably not really solve this for any class. This is a higher level type problem anyway, but I want you guys to at least see this. So it goes through a different type process, but it ends up being the exact same expression as the other side, the more conventional inertial frame of reference way of solving it. Okay. All right, so there you go. That was pretty fun. Okay, now let's get to the main course of today. You guys got this paper. It says Turntable Friction Lab. So when you guys get back to the lab area, there are all these turntables back there. There's also a bunch of items. So there's math plugs, there's some binder clips, there might be a paper clip back there, there's probably some guitar picks, there might be a Play-Doh canister. Okay. If you have some coins in your pocket, you could throw some coins on here. Right? All right, so lots of items to play with, right? And each of these items is different materials. Okay, so what's the coefficient of friction, say, between this math slug and this wood surface, or between this coin and the surface, right? Or this Play-Doh canister plastic and the surface? There's some coefficient of friction, which is like a material property. So do you guys think, here, if I get this thing spinning, right, all those objects you're seeing right now are on a circular path, which means that there's a net force. And that net force is what type of force? It's not a tension, it's not a weight, it's a what? Friction, right? Yeah, which is acting as a centripetal force. Yeah. So the friction force is acting as the centripetal force. So hold on to that idea because that's going to come back and play in a few minutes. Right? But see, if there was very little friction, then these items would be sliding off. But it looks like there's sufficient friction to be able to handle like that angular velocity. Right? What if I speed this up a bit? Now some of the outside objects are flying off. It looks like the inside objects are still on there. Okay, so maybe like the position of these objects, the radial distance from the center, had something to do with equation one way or another. Okay, you guys got some rulers. You guys can probably measure. Let's speed this up even more. Yeah, thank you. Right. Just think faster spin, and at some point, yeah, now we got stuff flying off. And it looks, oh, got a holdout. There we go. And finally, that one goes off. Whew. Do you think that that coefficient of friction could be determined just by what you just saw? Like if you can figure out how fast it's spinning and say its distance to the center, right, from say the center mass to like right here, like that give me so many centimeters, right? And you can figure out how fast it's spinning at the point where it breaks friction and slides off. There's probably enough information there to be able to, like in principle, figure out what was the coefficient of friction. So I'll show you guys how to do it, and then you guys will have the rest of the class period to figure this out. And so take a look here. Let's start by looking at this free body diagram. So zoom in here. I mean, this is the turntable. Notice I did omega for angular velocity. They could be like radians per second. Right? So it's spinning about this axis. Right? Now here's your item. Right? Might be like mass log, a point, something like that. And I gave you guys the free body diagram for it. So there's three forces while this is rotating. Right? Its weight, which is mg. The normal force, which is just balancing out that weight. Right? So I'll come back later. Okay? And also the friction force. Now, notice how I drew the friction force. It's a center-seeking force, right? It's the centripetal force. So as this is rotating around, right, the friction force is always pointing towards the center of the circle, and that's that one. Okay. All right, so there's the setup. Let's take a look at the table. So first column, trial. Go ahead and pick up one of those items and put it in the trial. So we got 100-gram slug. That could be this guy, 100-gram slug. We got if you have a coin in your pocket, you can specify what kind of coin because different materials, right? If you find one of these guitar picks around, right, from Songwriting Club, have that. There was a plastic Play-Doh canister, right? Maybe there's some binder clips back here, some paper clips, so maybe some clip of some kind. Right? So pick different items and say, hey, I wonder what is the coefficient of friction between, say, like that item and that turntable surface. Right, next column, gravity field. So that's going to be a number that matters because I bet you guys could probably imagine if you did that exact same experiment, say on the moon or like some surfaces, some different planet that had different gravity, it'd probably slide off at a different point, right? Okay. So you guys know 9.8 meters per second squared, but let's do what we did for the Atwood lab and just do centimeters today. So that's the same thing as 980 centimeters per second squared. That is the free fall rate of this 980 centimeters per second squared. Next column, radius. Remember, that's your radial distance to the center. So on my picture here, it's like from this axis of rotation to wherever the object is, right? So you guys have some rulers. Those here. Here's the center point. So right now I'm looking at about 8 centimeters right there. Right? But if I back this up, maybe this is like about 13 centimeters right there. Oh, well, I'm zooming in, but you can go from the center to the object, get the radius, right? Okay, so that's going to be important. You guys just saw why, because it looks like the objects that were close to the center were like the holdouts that were sliding off the last. Next column. Okay, now here's where the procedure kind of matters. So I did type a number in here, but I have to tell you what the thought process was behind that number. So you guys saw if you spin the turntable too slowly, nothing slides off. And then you speed up a little faster, a little faster, a little faster. You just do one item at a time, obviously. You don't have to have them all on there at the same time. So you want, at some point, your item is going to slide off. Okay? When it does, you want to figure out how fast is that spinning. And you can quantify that in radians per second, but we're going to sort of like build up and calculate that. Okay? So at the moment it breaks friction and slides off, try your very best to maintain that particular angular velocity. Okay? So suppose I have this going. Okay, so zoom out here. There we go. Okay, so it's too slow, too slow, too slow. At some point, I get fast enough, slides off, and then suppose it was like right there. Okay, I'm going around. Okay, then you guys brought your stopwatches today, right? You guys brought your cell phones. Right, so break this up and you go like, bam, bam, right, and calculate how much time is it for one revolution. Right, time for one revolution. You guys get the idea? Right. Now, Do you guys remember when you're applying equations, like those equations on the poster on the wall over there, for like rotational type stuff? You don't want to have numbers with degrees or revolutions. You want what unit again? Radians. Guys, 1 revolution. How many radians is that? 2 pi? 2 pi? Ah, that's what the 2 pi is, right? So your timing, how much time does it do 1 revolution? You guys get the idea? For that particular angular speed that it broke friction. Okay. Okay. Now, I'll tell you guys what. If you don't like that particular procedure, suppose you want to do like 3 revolutions. You want to time that. You could, if you want to, scratch this out and do 6 pi, because that would be 3 revolutions would be 6 pi radians. So if you want to do that, go ahead. But do 3 times and take an average, because getting the amount of time is probably one of the trickiest numbers to grab in the labs in this class, right? Like exactly how much time is that? Okay. So do 3 and take an average, right? And then if you figure out how far does it turn and how much time. So if you do 1 revolution, you can do 2 pi radians divided by that time interval. Okay? That would tell you omega, which is radians per second, angular velocity, how fast it's spinning. That's what this column is, right? You guys good so far? Who's got any questions so far? Because we're about to get the last column, which is going to give you the answer to coefficient of friction. Okay. All right. So to get coefficient of friction, at this point, you will have enough data to be able to get it. Right? But what exactly is the expression for the solution? So I went ahead and derived it for you right here. Right? So let's go through this derivation. I mean, if you want to get like the most from this class, you're really close. You could derive this from scratch yourself, but here, I'll take you through the solution. So you guys told me a moment ago that this friction force is acting as a centripetal force, and that's actually the first step, right? Now, do you guys remember from a few weeks back that friction force is coefficient of friction times the normal force? You guys remember that? Another way to think that is that the ratio of friction force to normal force is the coefficient of friction, right? Now we're looking at the moment that it slides off, it's like maximal friction. So this would represent coefficient of static friction specifically, right? Okay. So in place of friction force, I substituted in coefficient of friction times the normal force. Remember, the whole point of this lab is to figure out what is that coefficient of friction, right? Okay, so now we have what we're solving for. Okay. And how about centripetal force? Now, you guys did a lab with the canisters and the string and the pipe, and it got mv squared over r. But an alternate version of that is m times omega squared times r, right? And that's nice because, well, you kind of have omega already calculated at this point, right? Okay. You could go through linear speed v if you wanted to, but I just said it this way for you guys. Okay. Right. Okay, so this is equal to this. Is that okay? Right, so friction force is centripetal force. Right. Now let's go another step. You guys remember that normal force would be balancing the weight here? So I can take normal force and substitute in mg, right? You guys see that? Right. Now here's where, do you guys see the mass is going to cancel out? Right. Notice I didn't actually give you guys a space on the table to record the mass. I probably should have just for like scientific completion, but at least according to this, the mass should cancel out. You guys could test that though, right? Suppose you find different weights back there at lab weights that look like they're probably same material, right? You could try this out. Hey, have a big one, a small one, and see if they actually do come out to approximately the same coefficient of friction, right? The mass should cancel out, right? Brings you down to the step, right? And then all you have to do is divide down g, right? Gravity field of the planet, and you get this expression right here. So coefficient of friction, zoom in here. Coefficient of friction is the angular velocity squared, so how fast it's spinning squared, times the radial location of the object that broke friction slid up, divided by the gravity field of the planet. Okay. That will tell you what coefficient of friction is. Okay. You guys get that? Okay. So you'll have all those values. You just pop them in the calculator. Okay. I'll give you another detail before I send you off here. Okay. Suppose you and your teammates are all looking at the same data. You pull up your calculators and punch in some numbers. Right. And let's say one of you gets it right and 2 of you make some kind of mistake somewhere. Right. And you come up with 3 different answers for a coefficient of friction. Right. So look at these 3 numbers, 0.003, 0.30, and 300. Okay. Now, one of these looks pretty reasonably true, and the other 2 look way off. Guys, which of these numbers is the most reasonable coefficient of friction? Yeah, 0.3, right? Because remember, a way to interpret this is 30%. That's to say that this force is 30% of this force. And that should be approximately what you guys get. You might get 0.2 or 0.6, but it should be like somewhere kind of in there. Right? That's kind of what you're looking for. Okay, right, guess that. Right, so by the end of class today, just toss this in the gray tray. I think you guys would be pretty good on time. If you guys got any questions, let me know. I'll walk around, help you guys out. Remember, turn in your homework by tomorrow. Some of you guys turned in already. If you did, you can always turn it early. And your take-home quiz is due by Monday. Yeah, if you want to turn in tomorrow and have out of your hands by the weekend, then you can do that too. All right. So I'll walk around, help you guys out on this lab. and solve it for what is the coefficient of static friction. Yeah.
Why does it say under